All right. Well, good evening, everyone. Thanks for spending some time with us tonight to talk about rockets, my favorite thing to talk about. I'm going to talk tonight about how you do systematic flight testing in the American Rocketry Challenge so that you can use the data that you take and the knowledge that you have about aerospace to converge quickly on your performance challenge in TARC. It's rocket science. It's very systematic, and if you know what you're doing, this is a challenge that you can easily meet. But it's a challenge. This is not an easy event. It looks easy. Just build a rocket, put an egg in it, fly at 800 feet. How hard can that be? Yeah, it's precisely 800 feet, and it's precisely 40 to 43 seconds. That turns out to be hard. There's a lot of variables. And I'm going to talk about what those variables are, and then how you can control for them, so that over a period of some number of test flights, you can systematically converge on a repeatable performance that's at the objective. That's how you win TARC. It's very systematic. And in the process of doing it, if you understand rocket science, which is the whole objective of TARC, to make sure that you do, then you can do this, and you can do it really well. So I'm a co-founder of TARC long ago. I've been the NAR, National Association of Rocketry's manager for it from the very beginning, every year that it's been held. So I do the fun part, me and the hundreds of NAR members around the country who work with all of you individual teams to learn rocketry and fly rockets safely. Now that's fun. Our partners in the Aerospace Industries Association do all the hard work that isn't fun, registration, collecting money from corporate sponsors, and all the nuts and bolts that make the mechanics of this program actually work. And between the two of us, it's a great team, and that's how we keep TARC running. So let's get on with the discussion here. So this is a normal cycle for TARC. First, you learn the rules, you learn how to build a basic rocket, if you haven't done that before. Then you design and fly your rocket on the computer with the software, the flight simulation software and the design software, OpenRocket or RockSim. Then you build that rocket to your design with real stuff, wood, body tubes, plastic, real stuff you got to put together. You got to learn how to put things together straight. Then you test fly it. And at the end of test flying, you qualify for the TARC finals, and you come to the TARC finals and win. That's the cycle. We're going to talk about step 4 on the cycle tonight, which leads to a success in step 5. So why do you test fly? Well, believe it or not, your rocket might not work exactly the way the computer said. It might not work perfectly the first time, and it might not work perfectly the 9th time. And it takes a while to find all the different ways that a rocket can fail. Just FYI, I crashed a rocket this past weekend. I've been flying rockets for 58 years. I've flown that rocket 20 times. I found a failure mode in that rocket that I had never seen in my life before. It was a big rocket powered by a K motor. And, stuff happens, and it will happen. And you need to build up enough experience and fly your rocket often enough that you find all those odd failure modes that otherwise will probably happen to you either in your qualification flight or when you get to the finals. So practice makes perfect. Perfect practice makes perfect. So the computer software is really good. It gets you in the ballpark, but it does not exactly give you the altitude and performance you're going to actually get with your real rocket. I'll talk about why. So you have to flight test in order to actually figure out what the real rocket is going to do. And you can't just rely on the computer. And if the computer says it's going to go 800 feet, well, it probably isn't. It's probably not going to go quite that high. And there's some reasons why that is true, but you got to fly it to find the reasons correct for you. And of course, then there's always weather. The wind could be blowing, it could be raining. There could be heat-driven thermals. There could be lots of stuff that changes the performance of the rocket, changes the trajectory or duration of the rocket. And it happens, right? You can't control the weather. You have to simply adapt to it. And if you know what you're doing, you can adjust your rocket's launch angle or other characteristics so that you actually can ride through the weather and get the flight performance you need despite the weather. But you build up that accumulated knowledge of how to make those adjustments through test flying with careful collection and understanding of data. In past years, teams that made it to the TARC finals typically did at least 15 test flights. Some of them did 50 or 60. But you don't do it in 1 or 2 test flights. This year, there probably aren't going to be as many teams that can do that many flights. just because of all the restrictions we're living under for COVID. So maybe people won't on the average make 15 to make it to the finals, but they won't be making it on 1 or 2 flights. You can't get lucky and succeed at TART. You have to be good and you have to know what you're doing to succeed. You can get lucky on 1 flight, but you got to do it multiple times. And that is not based on luck. So here's some failure modes. This is not a comprehensive list. There are more failure modes than you can imagine. Non-vertical flight. Why does non-vertical flight happen? When you pointed the launch device straight up, hopefully you're using a rail, you have to at the finals. Well, you might have too light a thrust to weight ratio, where the rocket staggers into the air at low velocity and is very subject to wind, crosswinds, and just doesn't go vertically. You might have the launcher angled in the wrong direction because you didn't pay attention to what angle it was set for relative to vertical. You could have a wobbly launcher. You could be using a launch rod, which whips and flings the rocket in an unpredictable direction, which is why we don't use them anymore. Stuff happens. You can control all of these factors and make sure that they don't happen to you. But if you don't know what you're doing, they will happen to you. You could have an incomplete deployment of your recovery device, your parachute this year. But if you are systematic, consistent, and careful about how you pack it, you'll never have that problem. If you just stuff it in the tube and hope for the best, you will have that problem. You could separate the rocket into 2 parts. Remember, this year the rocket has to come down with all parts connected together. Some years we do require they separate. This year we don't. We require that they not separate. So when the ejection charge goes off, big bang, blows the top part off the rocket, and at the end of the connecting cord, that part comes to an abrupt halt. And if the cord has no elasticity in it, or is too short, or is not strong enough, or the place where it's connected to the rocket isn't strong enough, it'll rip out of the rocket, you'll separate. And that cord might get burned over the course of many flights, so it might be worn out. And that's one of those things that you only find, after 5 or 10 flights, that you weren't paying attention to the integrity of that cord and it got partly burned through and snapped on your 10th flight. You could break an egg. That could be due to insufficient padding. If you put enough padding around the egg, you can free fall it from 800 feet, but you can't really carry that much in your rocket. So you have to put some padding, and it has to be in the right places, particularly on the sides, because your egg capsule might land sideways due to the crosswind. And if you had multiple eggs, which we don't this year, you have to put padding between the eggs. And if you aren't careful about where you put the altimeter, the sharp corner on the circuit board of the altimeter will punch a nice little hole in the egg when the 2 of them slap together. So broken eggs can be completely controlled for. Broken rocket part on landing, well, these rockets do land at a fairly good speed. We pick a fairly short duration so that people don't have to fly on large fields, because it can be windy, and if you have a long duration in a high wind, you're going to go a long way. So we have a pretty brisk landing speed, and that stresses your rocket, so you need to make the rocket very strong in order for it to not break on landing. And first and foremost, the way to make sure that you avoid failure modes is to have a checklist to check to make sure that you aren't making the mistakes that lead to failure modes. That checklist will become longer with your experience. So you'll start with a short one, things will happen, and you'll add things to the checklist so that don't do that again, so that they don't happen again. Otherwise, you'll repeat mistakes. If you don't use the checklist, you will repeat mistakes through ignorance. So let's talk for a minute about computer versus reality. So the computer altitude prediction, I know you're shocked, isn't going to match the real altitude. It just doesn't work that way. Usually the computer predicts a higher altitude than your actual flight altitude due to one of a bunch of factors. You could have a non-vertical flight. The rocket could weathercock into the wind, or as I mentioned before, you could have the wrong launcher angle or a wobbly launcher. You could have a rocket motor that does not perform exactly the way that the representation of the rocket motor is done in the computer program. The rocket weight may not match exactly the weight that you used in the computer simulation, and that's a rookie mistake. You've got to know what your rocket weighs and do flight simulations based on the actual weight of your actual rocket, including egg, altimeter, and everything. Simulations that are based on the wrong weight are completely useless. So you need to know what the weight of your rocket is before your simulation actually has a chance of matching reality. Atmospheric conditions At launch site elevation will affect the air density, which affects altitude. The temperature will affect altitude somewhat. It changes air density. And of course, if there is a thermal wind, a vertical rising air mass due to atmospheric heating, that'll cause your duration to vary, but it won't affect your altitude. And of course, rocket drag, and that's probably the biggest variable. Your construction techniques may not be perfect. And so if your fin is slightly crooked or something is slightly misaligned, the rocket will have a lot more drag than the computer program thought, because the computer program thought that you built everything perfectly straight. And so, you know, if it isn't perfectly straight, it won't go quite as high. And you also experience flight damage, which tends to beat the rocket up a little bit and cause it to have more drag as time goes on. So the effects of motor performance in non-vertical flights can be minimized by paying attention. I'll talk about those later. As I mentioned, you have to know the actual weight of your rocket and atmospheric conditions. And if you enter those into the computer and use that as the basis for your flight simulation, then you will get a simulation that's closer to reality. And if it isn't still close to reality, after a few flights, when you have the real altitude that the rocket goes with that real motor, then you can go back into the computer and manually override the drag coefficient, adjust the drag coefficient so that the simulation predicts exactly the altitude that you actually went. And that's your real drag coefficient. And from that point on, you can then vary the weight of the rocket to change altitude, and it'll actually respond almost exactly the way the computer program says. But you have to have the real drag coefficient of the rocket in there to have that work. So this is not the Kerbal Space Challenge, where you don't have to build a physical rocket, right? So you have to build a physical rocket and fly it, and it won't do the same things the computer says it would. So one of the issues that would cause a variation in altitude would be weathercocking. Weathercocking is the propensity of the rocket to turn into the wind. If a rocket is stable with the center of gravity ahead of the center of pressure, when a side wind blows on it, it will rotate into the vector sum of the vertical velocity and the horizontal wind velocity. That's not straight up if there's any wind. And it will orient itself along that vector as it comes off the rail. And the faster the rocket's going, coming off the rail, the less propensity it has for that little wind velocity vector to push it off vertical. That's why you use a 6-foot rail. That's why we demand that you use a 6-foot rail. That's why you want a high thrust motor, because it comes zipping off the launch rail and it's going so fast that the wind velocity has much less effect on its vertical flight. It goes much straighter. So using a higher thrust motor is a good thing. I had a team propose to me the other day in a Zoom mentoring session that the flight simulation said that the perfect motor for their rocket was an F-12. I said, no, absolutely not. That has such a low thrust to weight ratio that your rocket will stagger into the air, and it has no chance of going vertical because the computer didn't know that. The computer, you didn't put a crosswind factor into the computer simulation. So you want a higher thrust motor, and you want to make sure that you come off the launch device with a real good speed, and a 6-foot rail is absolutely the way to do that. And a rigid device, not a rod, a rail. That gives you time to build up enough velocity that you're not going to be too subject to weathercocking unless the wind is really high. But you will be less subject than you would be if you had used a lower thrust motor. And weathercocking leads to different altitudes, right? So if the rocket doesn't go up straight, it follows a parabolic trajectory to apogee rather than a pure vertical one. And what you want to do is fly a pure vertical trajectory to apogee, because otherwise you have a cosine error, cosine of the angle from which it's off vertical, and that reduces your altitude. So if you weathercock, you will not go the natural apogee altitude of the rocket. Well, how do you avoid weathercocking? I gave you a couple ways: higher thrust motor, good long rigid rocket launch device. But you can also angle the rocket which way? Downwind, because the rocket weathercocks into the wind. And so if you angle the launch device 1 or 2 degrees downwind, when it weathercocks, it will go into the wind and therefore go straight up. This is really hard to teach. It's counterintuitive. You want to angle the launch device into the wind because you don't want to chase the rocket so far, get over it. What you want to do is angle the launch device downwind so that the rocket goes perfectly straight. This is a precision performance event. You have to have the rocket going straight up to get precise, repeatable performance. So you tip, now, how many degrees do you tip it downwind? Well, you got to figure that out by flight testing, by taking data on what your angle off vertical was versus what the wind speed was, and then watching the flight to see if it actually ended up going vertical. And making an adjustment, making yourself a little table. It will depend on the weight of your rocket, thrust to weight ratio, the type of motor you use, and other factors. The fin area of your rocket, a rocket with a very large stability margin, that is a very large distance between the center of gravity and the center of pressure, very heavy nose, very large fins. Those tend to weathercock more than rockets that have a smaller stability margin. So every rocket has a different response to the
Oh, we seem to have had a little bit of an internet error, so we'll give Trip just a minute.
Yeah. Did you lose me?
We got you back now, Trip.
Did you? How much I just said? Did you guess?
You had just finished talking about um, center of about rocket.
Any more? Yeah.
Correct.
So yeah. So your rocket's individual performance in response to crosswinds will depend on the stability margin of the and the thrust to weight ratio. And you need that. You need to figure out by taking data, by measuring the angle that your launch device is off of true, looking at the wind direction, measuring the wind speed, and then looking at trajectory and understanding, was that a vertical trajectory or not? Somebody has to step back some distance to see that truly. And yeah, that's a lookup table that you can make. So you know what to do. If the wind is 10 miles an hour at the finals, and you've got your lookup table, you know that if it's 10 miles an hour of wind, I need to angle my rail 3 degrees downwind, or 2 degrees, or whatever your data tells you. I've said the word data a lot. I'm going to keep saying it a lot. That's what this is about. Take data, understand what it's telling you, adjust based on what it told you, and test again to make sure you got it right. So let's talk about rocket motor variability. So the computer programs that you're using, the flight simulation programs, use average data that was taken by the NAR Standards and Testing Committee from production samples when the rocket motor was first introduced. Current production precisely match that. It gets close. The rocket from rocket to motor will not be perfectly repeatable. You see I circled on this slide the sigma, which is the standard deviation of the error as measured in the number of samples that were tested for this particular test report. So there is a little bit of variation. It can be 1 or 2% of variation in total impulse from one motor to the next. A 1 or 2% variation in total impulse will change altitude by 1 or 2%. This is just life. This is how it works. We're not paying NASA prices for rocket motors. We're not getting NASA quality. These are good rocket motors. They're not perfect. And so the only way that you can control for this really is to at least get all of your motors from the same production lot. They'll have the same lot code on them. This can be a little hard to do when you're doing, mail order, but if you have the ability to group your rocket motors in like production lot, then motors within a single production lot have far less variability motor to motor than motors between different production lots. And composite motors, the kinds Aerotech make, or Cesaroni, are more repeatable than black powder motors. Black powder motors are the ones Estes makes, good motors, but just the variability of composite is a bit less. So it's more repeatable performance. You also need to make sure that you use delay times that are long enough so that your rocket flies up through its ballistic natural apogee before ejection. I have a slide that will show you why that matters. So there's an altimeter curve on the right. That shows the change of altitude versus time. Altitude's on the vertical axis, y-axis, and time's on the x-axis. And you see that nice smooth slope going up to apogee where you see the peak of the curve. And then you see a little blip right after apogee. That's the ejection charge going off. So you want your rocket to fly this natural ballistic path to its natural apogee, go over the top, and then the ejection charge goes off. Hopefully shortly after apogee, but a few seconds after apogee can work too, because that changes your duration slightly. But if you have an ejection that goes off before the natural apogee of the rocket, you have changed your altitude dramatically. And so you absolutely have to have a delay time that's long enough for the rocket to roll over the top through apogee and then have an ejection event. You can compensate if the delay chart, remember you buy rocket motors with pre-made delays, reloadable motors, you can adjust the delays. So you may not have the perfect delay. It can be a little bit too long, and you just adjust for that by using a slightly bigger parachute. So it free falls for a second or so before the parachute comes out, and then you have a nice stable descent from a lower altitude than apogee. And so you can adjust for that, but you cannot adjust for having an ejection charge that goes off before the natural apogee. Delay times on rocket motors are not very repeatable. There's a much bigger error on those than 1%. And so you want to go a little bit long on the delay charge, because if you don't do that, you have getting altitude performance. Now, slope from apogee down is very smooth. That means that it had a constant throughout the parachute. Thermals, I'll talk about thermals in a minute, but if you change in the slope of that line, then you hit a thermal, and the rate relative to the ground changed suddenly because the air mass the rocket was in going up.
Trip, can you repeat your last point that you had about delay times? We had a little bit of trouble with your connection. We couldn't quite hear what you said.
Okay, yeah, so you want a delay time that gives you a flight that rolls through apogee before and is past apogee before the ejection charge goes off. So that tends to be a longer delay time on an E motor, 6 or 7 second delay. An F motor, 6, 7, 8 second delay. 4-second delays do not work for target. If you're using a 4-second delay motor, you are using the wrong motor. So somewhere in the 5, 6, depends on your rocket, but 5, 6, 7, 8 second delay is typical. But you can look at your altimeter trace. If you're using a peanut altimeter that has the recording capability, you can play back the trace afterwards and see, did your rocket have that nice smooth movement? As shown here, uninterrupted smooth curve that goes through the horizontal and then starts coming down. If you do that, then your delay time was good. If you have the ejection blip on the upslope, your ejection time was too short. So I mentioned thermals. So believe it or not, wind does not change the duration of a rocket much. You can fly in a 10-mile-an-hour wind or 15-mile-an-hour wind or no wind, and if there's no thermals, I'll talk about those, you're going to get basically the same duration. You'll have to chase it farther, but it'll be the same duration. Don't worry about chasing it unless you got trees nearby. But if you're flying when there is a rising mass of warm air, which tends to happen in afternoons, after the sun has been heating the ground for a while and parts of the ground get warmer than other parts and warm air rises, so eventually a bubble of warm air will break free from the ground and float upward, carrying everything in its path. And so your rocket, if it's in one of those thermals, rising warm air, will descend slower relative to the ground. It'll descend the same speed through the air mass, but the air mass itself is rising, so the descent rate relative to the ground is less. Could be a lot less. You could thermal the rocket away. You could put it in what we call a booming thermal, and watch it just sail away, and still be in the air 5 minutes later. You're having a bad day. So thermals happen in the afternoons, most places. Usually not first thing in the morning, most places, most times. I'm not sure about the desert. But around here in Virginia, certainly thermals are an afternoon thing. Not every afternoon. If it's not sunny, less likely to have them. But you need to think about that. So everybody wants to do their practice flights in the morning, fly practices all day, qualify late in the afternoon. What a bad decision. You're going to put your rocket in a thermal for sure if you do that. And your duration, your altitude may be perfect, but your duration is going to be out the window. So you don't really want to do that unless you are in a place where it's stone cold air and there's no thermals, in which case, great. But thermals are a consideration. You really need to think about that. They're hard to detect. There's instruments that can detect them, and some Rocketeers know how to do it. But if you're detecting them, you don't want to fly, right? Not TART, not qualification flights. So if there's thermals, you're almost wasting your time trying to do a qualification flight if they're thermals, because your thermals are of unpredictable duration and strength and location. And so if they're going on, you've lost control of your duration. Your altitude won't be affected, but your duration will be very much affected. So you have to be aware that they exist. Atmospheric density. So drag slows your rocket down, and eventually drag and gravity consume the energy that the rocket motor added to the rocket. And drag is proportional to the density of the atmosphere times the square of the velocity of the rocket. But density of the atmosphere changes. It is less when the air is warm. It's less if your flight elevation, the launch site elevation, is above sea level. And both of those factors can be accommodated in your flight simulation programs so that you know how much higher your rocket will go if it's warmer than standard, or if you're above sea level. You put those factors into the computer, and the computer will accurately predict what change that would make in altitude. And it's not insignificant. So if you're a team from Colorado flying at 6,000 feet and you were to fly in the finals at Great Meadow, which is 600 feet, you need to know what to do to make sure that your rocket, which went exactly 800 feet in Colorado, why does it go only 760 feet at Great Meadow? Well, the air is denser. But you could have figured that out before you came. Now this year, with the finals being spread all over the country, perhaps you'll be flying your finals flight at an elevation close to the one at which you practiced, or maybe not. Depends on which site you pick. But once you've locked your rocket in and got your performance on the mark at your elevation above sea level, get the flight simulation with the real drag coefficient and the real weight of the rocket, and go run it with a new elevation above sea level corresponding to where you're going to fly your finals flight, and see how much change that made in the altitude of your rocket. Or if it's 90 degrees when you do your finals flight and it was 60 degrees when you tuned your rocket and did your qualification, well, you know what to do. If the computer program will tell you what difference that'll make in altitude, and you can compensate for it by adding weight. And you can figure out how much weight to add with the computer program if you're using the right weight of the rocket and the right drag coefficient, and you've been measuring what the temperature was when you flew, and you knew what the elevation was where you flew. These are all things that you can measure. And if you understand how they affect flight performance and you measure them, you can figure out how to adjust so that your flight performance is exactly what you want it to be. There is always a slight variation in motor performance that you can't get around. So you're never going to have 800 feet on every flight just because you had 800 feet on one flight. You'll get 800, 805, 796. You'll scatter around that point, which is why we give teams 2 flights. And in fact, we give you 3 qualification attempts and take the best 2 to compensate a little bit for that statistical scatter, so that we don't have teams that get really lucky once making the finals or even winning at the finals. The finals this year, by the way, everybody who participates in the finals will be making 2 flights. And you may get lucky once, but you won't be lucky twice. You may be good, in which case you'll have 2 really good flights, but luck won't do it. And skill is based on measuring, taking data, and understanding the data and using it appropriately. Yeah. So make sure you take weather data when you fly. Humidity doesn't matter, by the way. Temperature matters. Barometric pressure doesn't matter very much within the normal range. If you're flying, in some kind of tropical depression where the barometric pressure is really, really low, the wind's probably really high. So normal ranges of variation in barometric pressure and humidity don't matter. Temperature does matter a lot.
Trip, we have one quick definition question from some folks that are new to TARC and Rocketry, and they want to know what the word apogee means.
Apogee,
it's important enough to stop the presentation.
Okay, apogee is the highest point of a rocket's flight, or the highest point of an orbit, if a thing is a satellite. So apogee is the place where where the rocket turns around and comes back down. Perigee is the lowest place. Now, perigee for a rocket flight is ground level unless you post hole it, in which case it's a couple feet below ground level. Perigee applies to satellite orbits. But apogee is how high did your rocket go? What's the max elevation of your flight? So flight testing is testing. It's data, taking data, understanding the data, understanding how to adjust for what the data tells you. Flight testing then repeats the flight and verifies that what adjustment you made achieved the effect you intended. And if it didn't, what did you need to change again to get onto target? This is a systematic, step-by-step process. Take the data, understand the data, use the data, change something if necessary, fly again. Do it again and again and again. If you're recording everything that matters about each flight, not everything matters, but rocket weight does. Flight characteristics, launch device angle, weather specifically being wind speed and air temperature. If you write all those things down and understand what they mean, and then write down the altitude and duration that you got, then you can figure out how to make the right adjustments in ways that I've explained so that you get the altitude and duration that you want. It's good to use a data logging altimeter, the Peanut, for example, to look at those traces of altitude versus time to more deeply understand what your rocket really did. We don't use those traces for score reporting. We only use the beeped out altitude. We don't have time to sit there and look at traces in the finals, but in your test flying, you should be using an altimeter. You should be using the Peanut, basically, an altimeter that gives you the ability to take data, look at data, and understand the flight. Did the ejection charge go off before apogee or after apogee? How long after apogee did it go off? What was your descent rate? Did the descent rate change? The slope of that downward line, did it change? You had a thermal. If you have one of these recording altimeters and look at the trace after flight, you'll understand some of what happened to your flight if it was less than perfect. And then you should have a computer simulation, ideally, that you can use on a laptop on the field, right? So if you don't go to the right altitude and you know what the, if you went too high, you know you need to add weight, you can verify how much weight to add by running the computer program again with that amount of weight and verifying that it makes the altitude change that you want. You can also do the computer runs in advance of being out on the field and build yourself a little lookup table or graph to do that. Either way, it involves systematic use of computer simulations using the actual weight and actual drag coefficient of the rocket. And then you can very quickly decide how much weight you need to change, add or reduce in order to change the altitude by some specific number of feet. Remember, when you change the weight of the rocket, you're changing its duration. If you don't change the parachute, it will descend quicker if it's heavier, but a few grams don't matter that much. They do matter a lot in altitude. They don't matter that much in duration. If you're adding 50 grams or something, that will measurably affect duration. But if you're adding plus or minus 5 or 10 grams, it won't affect duration very much. So my advice to teams is always to adjust your rocket to hit the altitude target first and get a duration that's somewhere in the ballpark. Get on altitude first and then start adjusting the recovery device to hit the duration target. If you're off altitude, then you're descending from some different altitude than your goal of 800 feet. So just the fact that you started from a different place means your duration is going to be different off target. So if you don't want to adjust two things simultaneously in methodical test flying. So adjust one thing at a time, get a reasonable sized parachute so that you're not staying up for like 2 minutes or falling way too fast, but then tweak the rocket to get right on altitude, and then tweak the parachute as appropriate to get right on duration. Remember, fly early in the day so that you're not dealing with thermals. There are a couple ways to tweak the parachute to get it on target. You can change the size. If you change the size, remember that changes the weight, typically, which does change your rocket's weight. So remember that when you've got it right on target in altitude, and then you change the parachute, you may have just changed the rocket's weight, which changes the altitude. Be careful. But another way that you can change the duration without changing the parachute is to just what we call reef the shroud lines. Tie a knot in the shroud lines partway up. That keeps the parachute from opening as completely and makes it descend quicker. You can't make a parachute descend longer if it's fully deployed and it's still not staying up long enough. You need a bigger parachute. You can also, if you want to reduce recovery, increase recovery speed, reduce your duration, you can cut holes in the parachute. That's irreversible. So that's not usually the best plan, but you can do that. Both that reefing and the cutting of holes are things where the change is empirically determined through flight testing. There is no simulation program that's going to tell you how those will affect duration. So there's a real need for significant flights to get data to make the empirical based adjustments to duration once you get to altitude. And you need to figure out, based on your data and your experience in various weather conditions, how to adjust your launch angle for different wind speeds, because you can't control the wind speed of the day on the day that you have to do your finals flight or even your qualification flight. You can pick to not do a qualification flight on a really windy day, maybe, if you don't run out of time first. But you need to know what you're doing and pay attention to that launch angle as a function of wind speed. So my advice to the teams is to test fly a lot, test fly as early as you can in the progression. Definitely waiting until the final weekend when qualification flights start your test flying is a plan. You should be test flying ideally, but COVID gets in the way, I know, for many. We're only just where I am in Northern Virginia, coming out of and launches, and schools are just resuming in-person education part-time. So everybody's behind this year. So that's why we extended the qualification flight deadline. So we're hopeful that there is enough time remaining between now and the deadline of May 17th for all of you to get out and do some flight testing before you declare your qualification flights and do those qualification flights. And if you do them well, we'll see you somewhere at one of the 11 sites for the finals. I always like to say in previous years that I'll see you at Great Meadow, but I won't. Not this year. But anyway, I think that's the end of my advice for today. I'm happy now to take questions, and I appreciate your attention during all of this. I'm going to quit sharing my screen, I think. Did the screen go black, or am I visible again?
The screen is still black. Here we go. All right. So thank you, Trip. A lot of tremendous advice in there. For everybody watching live, I hope you took good notes. And if you didn't, there will be a recording posted so everyone can go back, take a look again, and make sure that you're really getting all of that super, super valuable information.
And the slides are also posted on the TARC website in the resources section, and they have been for 2 years.
They've been up there for a while, so if you wanted a preview, you could have gotten it 2 years ago. So we'll go ahead and get to our questions here that we've had in the chat. Um, one question we have coming in from Sandra is, you mentioned lots of test flights. How many test flights do groups usually have in a year? I know you covered this at an early and towards the beginning, but they might have showed up a little bit late.
Well, our average for teams that made the finals is probably around 15. But there were teams that came to the finals that, oh my gosh, they flew 50 or 60 times. I don't know how they did that. There weren't too many that flew 3 or 4 times.
Yeah.
You just can't converge. If you're extraordinarily fortunate in your original design, you got lucky with your design, and the first time you flew it, it was real close to the target. Maybe you don't need that many flights, but you should plan on, there's no such thing as too many. But try to give yourself enough time to have 6 or 8 test flights before you qualify, at least, because you're just not going to find all the variables any sooner than that. And I mentioned that there is a statistical variation in motor performance. So if you're only flying 6 or 7 flights, you may never pick up on that statistical variation in motor performance. You really need more flights than that to get more statistical certainty that you really are, in fact, on target when you think you're on target.
All right. And speaking of getting ready for launches and scheduling launches, one question we have here from Yute is, do you have advice about weather and what the maximum wind speed should be to go ahead and do a test flight? So sort of making it a bit broader, at what point is the weather so windy or bad that you really shouldn't bother doing a test flight and wait for a better day?
Yeah, well, the NAR Model Rocket Safety Code says 20 miles an hour is the upper limit for safety, but that's too windy. If you're 15 or above, you're almost wasting your time doing systematic qualification or practice or qualification flights. It's just, they're going to be gusts. At first, the wind speed is not even all the way to altitude. It changes as a function of altitude, and it even changes in direction as a function of altitude. So if there's a lot of wind at the surface, there's probably more aloft. So I would recommend just not even bothering to fly if it's 15 or above. You love a calm day. That doesn't happen. Certainly never happens to us at the club I'm in. But 5 or 10 miles an hour, you need to be ready to fly at 5 or 10 miles an hour. You can't be waiting for a calm day. And if your rocket has a good brisk liftoff speed and everything, your 5 or 10 miles an hour isn't going to hurt you. 15 and up is going to be a problem.
All right. And we have one question from Cynthia asking about how to reef a parachute more specifically. It might be something that's a little bit more visual. So, do you have anywhere that we could point folks to learn how to reef their parachutes?
Not really. I mean, you tie a knot, so the shroud lines all come together at the bottom where it's connected to the rocket. Tie a knot in the shroud line several inches up from that point. That's a reef. It's called reefing. You can move the knot. If that didn't turn out to be the right duration, untie the knot and tie it again, higher or lower. Higher if you want to reduce the duration, lower if you want to increase the duration. It's completely reversible. That's reefing. That's what it is. It's just tie a knot and shroud lines. All of the shroud lines as a bundle together, not each one separately.
All right. And then we have an anonymous attendee asking, some of our parachute lines are too long and so we can't fold our parachute easily. Should we just cut or shorten the lines?
If you buy a commercial parachute, which most teams do, and I really recommend you buy a nylon parachute, they all come with shroud lines that are the same length. And if they're no longer the same length, that was you. If you made the parachute yourself, you should make it so all the shroud lines are the same length. Definitely the parachute's behavior will be unpredictable if shroud lines are all of different lengths. It will not, fill up as a hemisphere or a parachute, and its performance will be, very unusual. So they do need to be the same length.
All right. And now, speaking of parachutes, now talking about deployment, we have a question from Mehmet. How will we know if our chute deploys at apogee? So say a team doesn't have a peanut and can't see that graph. Are there visual indicators that they can look for or any strategies there?
Watch your rocket. I mean, the rocket emits a smoke trail. The delay charge sends a smoke trail out. If your eyes are good, mine are challenged a little bit these days from seeing rockets that are small at apogee, but Torque rockets are not small. You ought to be able, but you have to step back from the pad. Somebody has to be back 100 yards or so to really see the flight's trajectory. If you're underneath the rocket, it's very hard, directly underneath it, it's very hard to recognize apogee and whether the parachute came out at or after apogee. But if you step back 100 yards, if somebody from the team steps back 100 yards, they get a much better perspective and they can see whether the rocket arced over the top and began to come down and then the parachute came out. That's what you want to see. If the parachute comes out while the rocket has velocity going up, the rocket will stop abruptly, and that was too short a delay charge.
All right. And we have another question here. This is getting more into the construction side of things. But we have one team where their balsa wood fins are breaking on impact, even though they're confident they built them properly. And so they're asking for some advice on how to strengthen them.
Well, so balsa has grain lines. If you look at balsa wood, it has these little lines that go down the length of the sheet that you buy. You should cut the balsa fin out so that those grain lines are all start at the root where the fin is glued to the body. The line should go radially outward from that root. And if you cut the balsa in the correct direction with respect to grain lines, its propensity to break is much less. If you cut it with the grain lines parallel to the rocket body axis, it will break every single time on landing. The other thing you can do is to glue the rocket fin to the rocket with fillets, a bead of glue down the root between the fin and the body. After the fin has dried in place, then you run a fillet down that groove, that junction between the fin and the body, to reinforce it, to make it stronger. The ultimate way of making them stronger is to cut a slot through the body tube and glue the fin all the way through the body tube to the rocket motor, to the engine holder tube. A better solution is to not use balsa for the fins, but to use plywood or basswood. Basswood is pretty good, by the way, and neither of those has grain direction, so you don't have to be as careful about how you cut them. Plywood can be hard to cut by hand. You can laser cut it if you're fortunate enough to be in a school that has one of those. Most aren't. But basswood is a nice compromise where it's much stronger than balsa, less propensity to break, and not as hard to cut as plywood. All three of those types of wood are available at hobby stores, if there are any. But Hobbytown typically has a decent supply that includes those types of wood.
Mm-hmm.
Hobby Lobby, I'm sorry.
Yeah. And basswood is pretty easily available
Yeah.
online too.
Yeah,
I think you
all
can
this
actually.
is available online.
Mm-hmm. We have one question here from Melissa asking, our peanut trace curves don't look as smooth as the ones you shared. Should we be concerned?
Well, if they have lots of spiky noise on them, yeah, you should be a little bit concerned. You should probably get a different altimeter. That might be driven by the vent ports that you cut. If your vent ports are too large, read the instructions that come with the peanut, but if your vent ports are too large, you're going to have a lot of atmospheric or a lot of wind noise that resonates inside the altimeter bay and may create noise spikes. That could be a source of the problem.
Mm-hmm.
So typically, there's like 3 different sources. One is a bad altimeter.
Oh, we've lost Trip again. We'll give just a
Altimeter.
minute.
That's very rare. Perfect flight makes really good.
Sorry there, Trip. We lost you. You were about to say the 3
Yeah,
things.
so there's a couple ways. There are a couple of potential sources of noisy traces on an altimeter. Having vent ports that are too large is a common source of noisy data on the altimeter. Having an altimeter that can rattle around inside the compartment is another potential source. And a bad altimeter could be the third source, but typically, unless the thing's been crashed, Perfect Flight does not typically make bad altimeters. That's why they've been our vendor. So it's probably altimeter holes that are too large.
Mm-hmm. All right. And I just want to say, for a number of you who are asking some questions about what data should you record, or some of the other things there, I encourage you to go back and watch the recording, because some of the questions that are getting asked in the chat, I promise you, if you watch through one more time, your question has been answered. So we have got one here that wasn't answered from Eric asking, where should you put rail buttons on the rocket? Is it related to the center of mass or gravity?
Center of mass and center of gravity are the same. Well, you can have a really good debate amongst Rocketeers on that issue. Don't put them forward to the center of gravity. I mean, one at the center of gravity and one behind it by, depends on your rocket design, but yeah, 6 inches or so. So 4 to 6 inches. Maybe one at the center of gravity or slightly behind it, and enough spread between the two of them so that the rocket won't wobble back and forth on the rail. Typically, for TARC rockets, that's 4 to 6 inches apart.
All right. And one of the folks that registered ahead of time was asking about rail friction and if they should be concerned about any friction with their launch buttons and the launch rail itself, and if they should try and account for that.
It's not repeatable, and I don't know how to deal with it other than clean the rail. Right? If your rail buttons are straight, right, they're in exactly the same line, and that line is exactly equal to the center of the axis center of the body tube. If they're perfectly aligned with the center axis of the rocket and they're perfectly in line with each other, that rocket's coming off the rail fast and it's not going to have much friction. If your rocket rail buttons are canted a little bit with respect to the center axis of the rocket, you'll have a lot of friction because of the off-center thrust trying to jam the rocket on the rail. And so if you have a lot of friction, it's due to some misalignment, or a filthy launch rail. You can fix the filthy launch rail. Don't ever fly on one of them. Clean it off with steel wool or a Brillo pad or something. But typically, if there is a significant friction loss, it's due to a misalignment in construction, not due to sliding friction. Rails, there's a lot of free space between the rail button and the channel in the rail. There's no reason there should be any significant friction if your rocket is constructed with good alignment.
All right, so check your alignments, folks.
Yeah.
We've got one question here from Richard asking, how would you suggest adding weight to the rocket? What sort of material would you recommend?
There are so many answers to the question of what could you add. I've watched more creative things be done over the years to add weight to rockets, some of which I will not repeat because I really don't want you to do that. But, I have a whole collection of steel washers. I went down to Home Depot and bought a bunch of steel washers of all different sizes, weighed each one. And I have a pile of washers with weights written on them. And I just pick the washer that has the amount of weight that I want, or two or three of them added together has the amount of weight I want. You can use coins. You can use a little bag of sand that you can vary the amount of sand in. Whatever you use, put it underneath the egg, not above the egg. You want it down closer to, you don't want it to be crushed down into the egg. That's bad. The reason I said that is that you already have a nose heavy rocket typically, and you don't want to be adding lots more weight to the very nose of the rocket because you'll increase the stability margin to the point where it weathercocks too much. So it's better to put that ballast weight low, above the center of gravity, but not much. And typically the bottom of the egg compartment is the best place to do that. So that's where I'd recommend that you put whatever ballast weight. You will need ballast weight because remember the finals this year, your two flights at the finals, neither one of them is 800 feet, 775 and 825. Now you can use two different rockets, that's fine. But if you're using the same rocket, you're gonna have to change the weight of the rocket between flights. So you will be moving weight in and out. And it's the only way to change the altitude of a rocket is with weight. You can't do it with drag, balloon tensor or something like that. And get any predictable change. You have a change in altitude, but you have no idea what change. The solution on target and altitude adjust with weight. You have a flexible adjusting weight. Not installed, but flexible so that you can change the amount of weight that's installed.
So everybody, make sure that you're taking lots of data with how much ballast you're putting into your rocket, and that you're able to quickly and easily adjust for that. So this year's challenge only emphasizes more and more and more the need for good test flight data. All right, we've got you back, Trip.
Yep.
Awesome. And I will say I've also seen some teams use modeling clay as well because they're concerned about exactly where they were putting things. So you've got lots of options.
Yeah, modeling clay gets soft in the heat.
Mm.
So on a hot day, it'll tend to get gooey on you. It can be kind of messy. But yeah, sure, that works too.
You have lots of conventional options. Don't overthink it.
What you cannot do is be dropping your weight out at ejection. We've had teams do that where they poured a bunch of sand in the bottom part of the rocket and blew the sand or lead shot or something out of the rocket at ejection so it didn't affect their duration. Don't do that. That's really not right. You shouldn't be dropping stuff out of the sky on people who don't know it's coming. So make sure that your weight stays in the rocket all the way to flight termination.
All right. We've got one question from Puneeth here asking about, in order to reducing drag, asking, is it efficient to use elliptical fins?
Sure. This isn't about how to reduce. This is not about getting the maximum possible altitude out of your rocket. There are a lot of ways to design and build a rocket to maximize its altitude for a given amount of power. That is not what TARC is about. It's
Mhm.
about getting a precise altitude. So if your rocket's not going high enough and you're out of options for taking weight out of it, then you can try to change the drag by making the surface finish smoother. But the responsiveness of a rocket's altitude performance to changes like that is pretty slim. It takes a lot of change, and it's pretty hard to predict how much change you're going to get from changing the shape of a fin or smoothing a fin better. It will have some effect, but it's not likely to be large, and it's very unpredictable. So when you're designing the rocket originally, sure, use lower drag fins. You'll go higher, but that's not the point. The point is to
Mhm.
go precisely 800 feet, and you can do that with fins that are ugly, or you can use fins that are beautiful. If you use ugly fins, you just use a bigger motor.
Mhm.
Those are your choices, right? So this is not about maximizing performance. That's NAR, National Association of Rocketry Competition, World Championships are all about that. That's not what this is about. This is about precision performance. So you can build an ugly brick looking rocket, just add more power and it'll still go 800 feet.
Mhm. And for a number of the other questions that we don't have time to get to this evening, it really does all come down to recording all of your data and making sure that you can go back and see what changes you made and what changes happened over all of your test flights. If you're worried about what kinds of data you should be recording or what are the big things that impact your rocket, go back and rewatch this presentation, go back and look over the slides again. And that way you'll be able to see what you need to be measuring for. Ideally, you want to measure for as much as possible and then go back and see what didn't quite work. But it all comes down to trade-offs. You can have a perfect launch with bad fins. You can also have a great launch with less ballast than another team. There are lots of different design solutions, and it's up to your team to find what the right balance is from the design you started with. So we've got a lot of questions. We
Really?
do, yeah. We've got there are about another 30 that are
Oh,
still in the
yeah.
chat, and it's a number of them are things like, what is the qualification deadline likely to be this year? And the answer is it's May 17th. It's staying May 17th, and it's not moving. Um, so a lot of them are things of that nature, and then we do have one burning question that's on everyone's minds every year around qualification flight times, and it's about scores. And everybody wants to know what that magic number is.
I don't know. It's different every
Huh?
year.
Exactly.
It's hard to predict. So if you get a score of 0 on 2 qualification flights, you're in the finals. If you get a score of 100 on each of your 2 flights, you're not. And other than that, it's hard to say. A good score is, I don't know, 10, 20 on a flight. Remember, the score that gets you to the finals is the sum of the best 2 of
Hmm.
3 flights that you submit. So if your scores are, 20 and below, I'd be optimistic, but not certain. But it could be larger than that this year because there are fewer teams flying. There's less time to practice fly. So I would be surprised if the score this year was as tight as it has been in past years. Don't know for sure,
Hmm.
but there's a lot more challenges people are having to work through this year. But you can't qualify if you don't fly.
Exactly.
You can't make the finals if you don't submit a qualification flight because who knows, there may be only 100 of them submitted that are not DQs. And,
Hmm.
we don't know.
And really, even if you get to the end and you don't feel super confident in your rocket, fly a qual flight and send it in to us, because that's the only way that Trip and I even know that you built a rocket. And so if you're working and you've done all this hard work, unless we see a qual flight come in, even if it's a DQ, we don't know that you built anything. And that's something that Trip and I both care a whole lot about, is knowing who's building rockets and where, so that we can help make the program better in those places. And speaking of flights, we have one person asking how they schedule their qual flights. To which I would say, get in touch with your local section of the National Association of Rocketry. Go to the NAR's website, find the closest section to you, and reach out and see when they have uh, launch launches coming up. That is your best and easiest bet. Um,
There are other ways to do it, though. I mean, if you don't live near a section or they're not holding launches because of COVID, whatever, you can go off and do it on your own
hmm,
with an NAR member observing. It doesn't have to be at an NAR section launch. It just has to be at a safe place where you have permission to fly with
mhm,
an NAR member, adult member observing. That adult member can't be related to anyone on the team and or an employee of the school that's sponsoring or the organization that's sponsoring the team.
mhm,
Basically an impartial adult, but that person can join the NAR the day before just for the purpose of being the observer. If everything else fails and you can't find any other way to do it, but you got to go do it at the high school football field with a local observer, that you can do that.
yeah. And we have the instructions for doing that and exactly what you need to do on our website and our frequently asked questions page. So make sure for a lot of folks that are asking about the structure of the competition, read the FAQs. We've got dozens of questions up there that we get every single year, and we promise we've got good answers up there for you. Um, I think that about covers it for the things that we want to get in touch, that we want to cover here on the webinar. A few of you have asked some really specific questions about specific designs that I've typed a message to you and asked you to send us an email. I'll pass that along to Trip and you will get some specific advice. Um, Not necessarily we're giving anyone special answers, but we don't need to talk about control systems and complicated things like that on the webinar right now. Um, but I would like to say a huge thanks to everyone who attended, and that this will be posted on our website shortly, no later than next week. And Trip, thank you so much as always for your time tonight and everything you've done for the program.
Well, I like doing what we do here. This is the most fun I've had in my entire rocketry career. I really like showing young people how to build and fly rockets and watching them learn from the experience. That's why we do TARC. So thanks for hosting this tonight. Thanks to all of you for attending.
All right, everyone. Best of luck with your qualification flight launches, and we'll be in touch with all of you soon. Good night, Trip. Take care.